Okay, in this corner plot, yeah, in the phase histogram plot, the dotted lines are, is it the prior that we set previously?
The dashed lines?
Yes, the dashed line.
No. So those are the 1 sigma interval, the confidence interval.
Okay, 1 sigma.
So
Yes,
if
yes.
you want,
Okay.
if you want the prior, I think if you put priors equals true when you make the corner plot, it will then plot out the prior as well. Yes, sorry, it should be priors equals true, not prior equals true. I think this is a typo.
Okay, priors equal to true.
Yeah.
Okay. Yes, and another thing is that yes, in this salience quotient, where can I find this one? I'm not able to find this one. Sample equal to uni f.
I think, apologies, I removed the sample equals unif at some point, and then I didn't update the challenge question. So I think you just like don't worry about the sample equals part. Leave that and just play around with the. So if you add NACT equals 1 and walks equals 1 and things, it will speed things up.
Okay. Thank you, Tim.
No problem. Okay, so I'll get going. I didn't realize I forgot to put my video on. I should also say if others want to add videos, it helps me to be able to see faces, but only if you want to, of course. So hopefully you can see my screen here. So I'm back on the main GitHub page, and so we obviously yesterday went through sort of Bayesian inference and gravitational wave parameter estimation using the Bilby the Bilby Python API. So we were really down in the guts of the code. And then today we're going to be thinking about, how we can do this at scale. So I know that this is maybe going to be a little whirlwind, especially for people who have never seen any of this before. So we're going at quite a breakneck pace. So that's, just keep in mind that, don't be shocked if things are going really, really fast. I think the idea of this workshop is just to cover material so you can then come back to it in future. And this actually, I saw it just in the chat just now, someone suggesting that there could be some sort of chat to it in order to continue conversations afterwards. I think that's a really great idea. I don't know if Shashvath and people have ideas on that, but I would definitely encourage that because I think some way to communicate afterwards is very powerful. So so today then we're then going to get into Bilby pipe and clusters. So I've just prepared a quick sort of presentation of a few sort of key elements before we get into the main material. So kind of an overview is we're going to be using Bilby pipe. So Bilby pipe is a specialized tool for performing very common gravitational wave parameter estimation tasks. So you can't use Bilby pipe for sort of generic inference problems. It's really just for gravitational wave problems. You can use it. It's designed for use for large scale tasks. So things like simulate 100 events drawn from some prior, generate posteriors from all of them, and then maybe do some sort of task afterwards, like create a PP plot or something like that. And so because it's 100 events, each one can take a day or something to run. Generally, this is used on sort of computing clusters where you have access to many hundreds, if not thousands, of machines. But at the same time, you can use it on your local machine. In general, you'll probably just run things sort of serially, one after another. But it can be a nice interface if you just want to do sort of simple tasks like run something and you just want a simple ini file to do that. And we'll get into what I mean by ini file in a bit. So one caveat, and there's a question on this yesterday, but just to reiterate, there's another code after this, which is called Parallel Bilby, which is a specialized tool for using massive parallelization. So an example might be, running a very expensive waveform model, and you take over an entire cluster. So you're using, 800 nodes of a CPU all at once. So as I say, that's a very specialized tool. If you have access to such computing facilities, then you can click on the documentation. It's not as well documented and it's not as user-friendly at the moment. That's something that we plan to do in the future, but right now it's a very specialized tool, so it requires some kind of digging in and just figuring out things as we go. So we're not going to sort of cover that today. But okay, so then the plan is then to go through the workshop materials together. So I've put together a kind of README file which goes through basically getting set up with Bilby Pipe and also running one or two simple jobs. And then what I suggest is that we go into breakout rooms and we'll run those things interactively. What I'll do as I go through the workshop materials is I will essentially go at a pace where I think that you can follow along, but you should feel free to not follow along and just listen. Or if you want to try and follow along, please do so. And if you sort of hit things as we go, you can ask questions in the breakout rooms with the tutors who are very knowledgeable on all of this. So with that, I'd also just add that everything that I'm going to do is going to be sort of in the terminal, so not using the notebooks anymore. So you will need the sort of setup in your terminal. If you don't have that, we can get that set up in the interactive session. So don't worry too much if you can't sort of follow along interactively. Okay, let me just actually get the chat open so I can see things. Okay, Shafas. Okay, we can talk about the chat perhaps afterwards. Okay, so let's head to the workshop materials. So this is linked off the main page here of the GitHub. So it says getting started with Bilby Pipe. So let me click that. And let me just make sure, so to try and make this page a little bigger. Can everyone read the text okay? Is that a reasonable size?
Yes.
Yeah, okay, lots of yes, that's good. Okay, so as I say, this is going to be using Bilby Pipe, and everything is going to be sort of done in a terminal. So what I'll do is I'll open a terminal up and I will sort of do some of these steps interactively so we can see things kind of as we go. And so the first thing is, of course, installation. So if you are on sort of your local machine or something like that, if you follow the installation steps, you should have it already. But it's relatively easy to install, so it's just a case of pip install Bilby Pipe, and that will pull the latest version from the PyPy server. So you'll get something like this, and you can check that things are installed by doing Bilby Pipe -- version. And so this will print out some sort of message like this. If you have the latest version, it will be Bilby Pipe 1.0.1. There was some recent small upgrades, which were mainly based on sort of Slurm backends and things like that, which I'll talk a little bit about in a second. And you should also see your Bilby version that's printed out there as well. So I have the release version here. Okay, excellent. So then, so that's sort of checking it's installed. A kind of, I guess, a prerequisite for something that will happen down the road as we access data is that if you're running this on the LDG, so the LIGO data grid clusters, all the data is stored locally, and the libraries that we use are able to find that data and read it in, and that's kind of the ideal way to operate if you have access to an LDG cluster, is to do things on there because it's very fast to read the data. But if you run on your local machine or on a cluster which doesn't have access to the LDG data locally, it will pull the data in remotely, and all of this kind of happens under the hood. However, it is I guess it's worthwhile just knowing that sometimes this is somewhere where things like Bilby can fall over. Okay, and just looking at the chat, so Nikhil says some people may get import error, failed to import any Qt bindings. I think so. Nikhil, are you talking about the tutorials? Because I think we're on to Bilby Pipe where we're not using Colab.
Sorry, can you hear me?
Yeah, I can hear you. Yeah.
Yeah, awesome. So I just tried to install it into a new virtual environment because I had a previous version installed somewhere else. And when you install it again, some people might get if you just, because I think PyQt5 might not be a requirement. So if you don't have that installed and you try to import Bilby Pipe after installing it, you might not have it working. So you have to install this additional package, which is PyQt5. Or
Okay,
use
all right.
Colab or something.
Okay, thanks. Yeah, I don't think we want to use Colab at the minute because we're going to be sort of trying to do everything in the terminal. So I don't know how well that will work.
Yeah.
But if people know how to
Sure.
use that, then that's fine. But yeah, okay. So if you have that issue, then you can just install PyQt5. And so, okay, then Shrashti asked, can we install Frame CPP and NDS client outside Conda? So, okay, this is somewhere where the answer, as far as I'm aware, is no. So the basic kind of problem here, and this is why I really recommend people use Conda, is that these libraries are not Python libraries, they're C libraries. And so pip is a Python package manager, and it just cannot handle non-Python libraries. So you can install these things, but you need to basically follow the detailed instructions, and it's sort of you compile the C yourself. So it is possible, and if you know how to kind of do that, then please go ahead. But in my experience, using Conda is a lot easier to install these things, and that's the kind of recommendation from the LIGO computing folks who I sort of rely on for telling me how to do these things. So yeah, answer is yes, but with some difficulty. But if you know how to do that, then please do go ahead. I'll also add that you don't need these necessarily. You can. So if you have issues with getting hold of the data, what you can do is, and you don't have the data locally, you can actually just write scripts to kind of copy data files and create GWF files wherever you want, and just copy those files and then point your Bilby pipe jobs to local data files, and then you don't need any of these tools. So that's an alternative option, but an ideal one is to use Conda and install these things. An unfortunate one, of course, if you have used virtual environments before, but maybe for the time being, to get a workaround. Okay, great. So let's get into the basics then. So I've already sort of shown how to check versions of Bilby pipe and things like this. Now, so as we go along, I've put these little rockets in with some sort of tasks. And so if you're following along, feel free to kind of do these and check that things are going. And if you have problems, you can throw them in the chat and I can try and debug them online, although we shouldn't probably spend too much time on that because we'll be able to do that in the interactive session as well, of course. So in general, Bilby pipe operates through what's known as an ini file. You can also often refer to this as a configuration file. And we're going to see details of that as we go along. But in general, it's sort of a simple text file which you can easily share around and will reproduce very complex analyses, is the way that you can think about it. Now you can see the full set of options for the ini file by running this Bilby pipe -- help. And so if you run this, you'll get a huge sort of list of output. It's a little ugly because I've made this so big. It's very long. It's sort of makes it very unreadable and very dense. But you just can kind of search in that for the things that you might be interested in. So for example, there's a set of injection arguments if you want to inject signals into the data. If you're following along and you don't have access to a terminal with Bilby pipe installed, you can head to the documentation for Bilby pipe, and that's linked here. And this has now, so Bilby pipe -- help, it has all of the outputs here. And so this is quite useful if you ever sort of just want to show people. You can head to here and grep for things, or Control F to find sort of various bits. But so I guess the point I want to get across is, Bilby pipe has a lot of, there's a lot of different things you can do with it. It's not exhaustive. You will eventually find limitations. And this is, some of these limitations are by design, that we don't want to have the workflow be too complicated. So a good example of that is, you know, we often get people asking, well, can I get Bilby pipe to run 3 different samplers on the same job? And we made a design decision that we wouldn't do that. And the reason being, it causes kind of internal difficulties with how things are set up. And we decided it was easier for people to just write 3 ini files with the sampler changing between them and run them if people needed to do that. On the other hand, you will hit some cases where you know, you'll come across a workflow which we haven't thought of before. You know, I can't think of one off the top of my head, of course. If you do find something that you can't do with Bilby pipe, or at least isn't obvious how to do it, that's the case, you know, please ping us, open an issue. And it's likely that it's a case of just figuring it out how to put that in and provide a nice interface to it. Everything is possible with Bilby as sort of under the hood, but not everything is implemented, and that's, yeah, as I say, we try to make it so that we implement as many common workflows as possible, but we avoid making things overly complicated in order to make it sort of easy to use. So okay, so that's the full list of inputs then. Let's head back to this page. So if you're running at home, you've perhaps run Bilby pipe -- help. So now let's get into, you know, what are these ini files and what do they look like and how do we put things in? So the ini file, as I say, consists of just pairs of key equals value. And the key will be the things which are in that -- help. So for example, the key might be injection, and then you write equals you know, true or false in this case. So it's a Boolean, it takes, you know, either just a true or false value. On the other hand, you might have an injection file you put in there, in which case the key would be injection file equals, and then you'd have a path to your injection file, and so on and so forth. So let's then get into an example. So this is an ini file which is for injecting a simulated signal into Gaussian noise. I should just add quickly that all of the ini files and things that I'm going to present here are available in the repository under this pipe examples directory. So this one is bbh simple example.ini. If you ever want to sort of just copy those files, they're there, or you can just copy paste them from here. So what I'm going to do is I'm going to go through each of these lines in detail and hopefully give you some sort of sense of what each one means. So, okay, so the first line that we see here is an accounting tag, perhaps the most boring, but if you're running locally, you can ignore this. And if you're running on a Slurm cluster, you can ignore this. And I just realized I haven't got to talking about Slurm and HD Conda, so maybe now's as good a time as any. So, no, in fact, no, sorry, I realized that I have left this below as an item, so I will talk about that later on. Let me continue with just talking about the accounting tag. So the accounting tag is something which is used on LIGO data grid clusters, and it's a way to basically track what computing is spent. If you're part of the LVK collaborations, then you'll know about this and you'll know what to fill in. If you're new and you don't know, then there's a link here which you can follow to determine which tag you should use, or you can ask your collaborators and they'll be happy to help you out, no doubt. But as I say, for local jobs like we'll be running today, you can ignore this this element. Okay, then the next one is a label. So this is just a simple label. It's useful to remember what the job was for. You then have an out directory. So this is a relative path from where you run it. So this will create an out directory below the ini file, if you like, or in the same directory as the ini file. You can also give an absolute path and it will be created there if you want to put it somewhere else as well. We then have, okay, which detectors do you want to use? And so in this case, we're going to use H1 and L1, but V1 is of course also possible. And I think K1 is also implemented. I forgot to add that. And hopefully we'll have more in the future, of course. We then have the duration of data to analyze. And so the duration is just the duration in seconds. Again, if you're sort of not familiar with how to choose these things, it really comes down to the mass of the system. And you know, heavier mass systems are shorter, and lower mass systems require longer durations of data. in general, we always use powers of 2 for various reasons, but you don't have to use powers of 2. You can, in fact, use any duration you want, but in general, it's recommended that you stick with powers of 2s, just because other codes kind of use that, and so it's good for reproducibility. We then have the option to set which sampler we want. So in this case, we're going to use the Dynasty sampler, and we have the option to pass in sort of the quarks. So these are the things which you would usually add to run_sampler. You put here into a dictionary. So I'll just comment quickly on this. So the dictionaries that we put into Bilby pipe are really very flexible. So this is actually formatted exactly as a Python dictionary should be, with the key being a string, and then you have an integer on the right-hand side here. But because we know that people make typos all the time, and we don't like sort of forcing people to fix their typos, you can actually be very lazy with this. The colon sign can be an equal sign. You don't actually have to put quotations around here, all sorts of things. So you'll notice that often things work even when you have typos, and that's by design. Shashvath asked, could we add future detectors like Cosmic Explorer, Einstein? Absolutely. So the detectors is actually a Bilby thing. So it's so long as the detector is defined within Bilby, you can use it. And so if you want to add, a random detector somewhere, you can in fact add it within Bilby in your local copy, and just access it through this. There is a set of detectors which already exist, and you can go and look at that in the Bilby documentation as to which ones you can use already. It's just the ones which we looked at yesterday. So when you get empty interferometer, anything available there is available here. I will just say, so some of those like Cosmic Explorer, I'm forgetting exactly what the design of that is at the moment, but some of them have slightly different designs, and I don't know how up to date the Bilby implementation is with the current design. So sort of caveat that that as that evolves, you will need to sort of check and make sure that Bilby keeps up to date. But absolutely, we can do all of that. Okay. So yeah, so I was just saying about the sampler quark. So you can stick a whole bunch of different things in here, and this brings me to a point which is, this is one of the kind of opaque points of Bilby, is that these quarks are a little bit of black magic, which you kind of have to be in the know to know how to set them. There's a useful trick though, which is we have a method to learn about which ones are available, and I'm just trying to remind myself where it is. Sorry, give me one moment. I thought that we had this option. It's okay. I think then. Let me just. I'm going to check in the Bilby documentation. Sorry for doing this live, but it's something that I know a lot of people have questions about, so it's probably worth just looking briefly. Okay, the sampler help. Okay, so actually, my apologies. I think that this isn't so easily accessible from the command line. But okay, so what would I recommend if you want to know what to put in to this sampler quarks, is to go and look actually at the Bilby source code itself. That's in fact the sort of kind of most definitive thing. So if you head to the main Bilby repository, so that's here. It's the source code is supposed to be read of Bilby. It's we try to write it in a way that is easy to read, and encourages people to get involved in it. So I'll walk you through how to find it. So if you click on Bilby and then click on core and then sampler, you'll find all of the different samplers, and this is where they're implemented. And if you click on one of the samplers, what you'll find is a sort of, okay, there's a few different things in here, but there's always a main class which is called Dynasty in this example, and the documentation for it should be extensive and exhaustive. And so if you look through this, you'll find the other parameters, and this is then essentially a list of all the different things that you can pass in. So there's dlogs there, there's walks, and also sort of descriptions of all of those. And so we try to keep those up to date. If they're not up to date, then please let us know. You'll notice that for Dynasty, this is described as endpoints, but you can also pass in nlive, nlives, n_live points, whatever you want. Again, this is one of these kind of easy to use aspects where we try and accept whatever the user puts in so that you don't have to sort of remember which one goes for which sampler, as they have sort of different names in different samplers. Okay, so that should sort of hopefully give you a pointer as to where to look for these things. It's always the other parameters, and if things are missing, please do let us know. Okay, so then let's go through the rest of this ini file. So we have the prior file to use. Okay, so this is something I'm going to touch on in just a second, which is what these prior files are. But in general, this is just pointing to a text file on disk, and it can be a relative or absolute path, whichever you want. And as I say, I'll explain more about that in just a second. We then have, okay, so we want to inject a signal in this case. So we say injection equals true. If we don't say anything else, it will randomly draw a point from the prior and just inject that. So if it has no information about what to inject, it will inject a point from the prior. We'll see examples later on of how you can actually specify an injection file or an injection dictionary, which is specific injection that you want to put in. We then say, okay, we want Gaussian noise. And then there's a, the key here is that this is going to use 04 design sensitivity curves by default. If you want to change that, you'll want to change the PSD, which is by default. And so you can point to any PSD you want. So if you, for example, take the 150914 PSD, which was released in the open data release, and point, the Psd Dict. Let's just show where that is. So if you grep for PSD here, you'll find that there's a Psd Dict, and that's a dictionary of PSD files to use. And if you point that to the different H1 and L1 detectors, you'll then inject into 15094 like noise. Okay, I see a question from Sudi. So are these 04 design curve detector specific? Yes, so there's a Hanford and LIGO have the same 04 design curve. These are the ones which are in the so the LIGO, Virgo, Cagra observing scenarios document is the living review. That's where we get those from, and they're stored in the DCC. And if you sort of dig into Bilby, you'll find exactly where they are, and they'll sort of link to it and things like that. And yeah, so there's then one for Virgo, as that will have a different design sensitivity, and one for Cagra as well, of course. Okay, but yeah, if you're doing sort of design studies, that will be something you want to be very careful about, is make sure you use the right PSD. If you're talking about different configurations, they'll have different design curves. And so, we provide these defaults, but, if you're sort of doing studies, you want to be very specific about exactly which PSD you're using. And so I'd recommend, putting in which PSD exactly you're using and doing that explicitly. Okay, so then we have a few kind of options here. So the first one is the number of simulations. So in this case, we're just going to do a single simulation. It'll do one job if you like. If you want to do 100, you just make this 100. But because we're going to, we just want to run things quickly, we're going to set that equal to 1. And then, so I wanted to talk on this before. So I've talked about this in the question and answers yesterday, but I want to reiterate on this point about the different parallelizations, because I think that it's confusing. The documentation is explicit, but the kind of naming conventions I think can be confusing. So we have a parameter called n parallel, okay? And so what this n parallel does is it says, okay, run some number of identical jobs and combine them at the end. And so this, I said about this yesterday, and the idea is that you basically improve the convergence, if you like, of the runs. So you can run, and especially if you have access to a sort of a cluster where you have many thousands of cores available, run 4 jobs as a standard, is that we use 4 jobs for most publications, and then combine them. And in general, that will improve your sort of results. You'll end up with more independent samples and smoother posteriors. So that's a good option to use, especially if you're sort of doing production runs. If you're just doing testing as we are here, and you just, you don't care too much, then m parallel equals 1 is the right way to go, because you don't want to run waste computing time. There's then a separate level of parallelization, which is the parallelization for a given job. And so this here is the request CPUs option. So request CPUs says, okay, run this job, but use 4 CPUs to do the sampling. And so there's a few different samplers which this is enabled on. Not all samplers it's enabled. At the moment, it's Dynasty, CPNest, and PTMC or TEMC. Those 3, I'm certain it works on. There are others, I think, PyMultinest, there's some efforts ongoing, but I haven't tested it myself, so I wouldn't like to say that it's how well it's working. But those 3, at least, certainly, and certainly with Dynasty, this is very effective. And we've shown that we have almost linear scaling with the number of CPUs. In general, if you use 2, it's actually slower than if you use 1, and this is due to the overheads. If you use 4, it's a little bit faster. If you have access to sort of 16 cores, that's where you really start to see the benefits, and so that's where you really want to be using this if possible. Okay, just one final bit on that, and then I'll get to the questions. So when you use this parallelization, so in this ini file, I've commented it out, and that's just because if you run this locally, you may not have access to so many CPUs, so I didn't want to sort of crash people's computers. But if you uncomment it and put this, for example, when you do your run, you'll see setting up multiprocessing pool with 4 processes, and that's a good check that things are working. Okay, so now let me just get to these questions. So does 4 jobs mean running 4 parallel chains? So is that the n parallel option, Nurban? Nurban, yeah, yes. Yeah, so yeah, it's exactly that. So it's, let me just get back to the question. I know, sorry, it's not 4 parallel chains. So it's not MCMC. It's literally take the one job that you've set up and run it identically 4 times with 4 different labels. So you really run, like, if you're using Dynasty, you run 4 different Dynasty jobs. If you're running MC, you do 4 different MC jobs. And then you combine them together at the end. And so when you run it with n parallel equals 4, you'll see 4 different trace plots, 4 different results files, and everything else. So then Suri asks, do you multiply posteriors from all these parallel jobs? So you don't multiply them. What you do is you effectively just combine the samples together. So if I have 5,000 samples from run 1 and 5,000 from run 2, we put them together in one posterior. We'd sometimes do some sort of sampling and things like that just to improve things where that's needed. And the evidences get averaged. So in general, your evidence count estimates will go down because you're averaging over many runs. Okay, does N simulation refer to different jobs? Slightly confusing about what the difference between M simulation and M parallel is. So from Bhaskar. So N simulation is the number of different jobs I want to run. So let's imagine that I want to do 100 different simulations. Then I'll say N simulation equals 100, and it will draw 100 different points from the prior, and we'll analyze each of those. So if we have M parallel equals 4, for example, then we'll analyze each of those with 4 different chains. And then just to add to the confusion, if we add sort of request CPUs equals 16, each of those jobs will be using 16 CPUs. So this is sort of a warning. You can very quickly use a lot of computing by changing these numbers, right? So if you have, N simulation equals 100, M parallel equals 4, well, now you're running 400 jobs. And then if you have request CPUs equals 16, you now have 400 times 16, so 6,400 CPUs that you're using for however long it's your compute time. So you can use a lot of computing very easily with this. how does the multiple CPU option auto-specify parent and daughter jobs? So the multiple CPU option does a, we use basically a, there's a 0th node, so there's no decision essentially. If you give it 16 cores, one of them will be the parent, and then the others will be the daughter jobs. So it's kind of auto-selected, I guess, by the code under the hood. There's probably some indexing to it. Does the scaling with CPUs work well in normal Ethernet clusters also? Okay, so with this, so this scaling is happening so when we use Bilby pipe, Ajith, we're doing things on a single CPU, and that scaling, you know, we do see very good scaling, and so there's no sort of question there about the Ethernet sort of connections between the different CPUs because we're only on one CPU. I know that, yeah, again, this is a place where the terminology is confusing. We inherit this from HT Condor. Request CPUs really means request the number of nodes on a CPU. I know so apologies, this isn't ideal ideal notation, and Stuart Anderson has made this point before, but we used HT Condor's definitions. So in parallel Bilby, where we operate across different CPUs, we see the same linear scaling, and so you can see that in the Parallel Bilby paper. We've tested that on, the Slurm clusters available to us, so the OzStar cluster, which has a good high interconnect, and yeah, we see very good scaling. Of course, if it's you know, a slow interconnect, then you'll still get linear scaling, but it will just be a poor linear, so your gradient will drop off, if that makes sense. Aranava, hand up. Yeah, please go ahead.
Hi, Greg. Sorry, I'm just speaking it out. Yeah. So I think there could be two ways of making things faster and more reliable. One is by increasing the number of jobs, independent jobs, and subsequently combining the posteriors. The other thing might be using parallel temperature change. But in your experience, which one is more more efficient for a given, say, 16-core processor? Do I make sense?
Yeah. So the parallel tempering is something which we do in MCMC. So in general, I think the parallel tempering is an absolute requirement for multimodal posteriors. So you have to have parallel tempering at some level. So my experience is you choose, you know, if you're doing MCMC, you need the number of parallel tempered chains, choose the minimum that you can in order to get the posterior correctly, and don't sort of do more, because effectively you're sort of wasting likelihood evaluations on these likelihood surfaces which aren't the one you're interested in, because you've raised them to some power. And then, you know, if you have sort of 16 core nodes, like the most efficient things, if you want to reduce the wall time, is use as many cores as you can on every single job, and then use as many as many jobs as you can. So if you can do, you know, an ideal scenario is 4 16 CPU jobs, that's kind of the fastest thing that you can do. Does that make sense?
Yeah, kind of. So I think it's something like intermediate. So few parallel temperature chains and combined with few independent jobs. Is that what you are suggesting?
Yeah, exactly.
Okay, thanks.
Okay, and then Surya asks, can we specify a particular distribution to pick up prior values instead of a default random uniform distribution? So it's never a uniform it's never a random uniform distribution. Okay, so the jobs are always picked for these simulations with whatever prior you pass in to the prior file. So if you use, you know, this example, it will pick values from that prior. Now you can look at what options you have by just grepping for the prior. And so you see there's a few things here. So the ones of kind of main interest are the prior dict and the prior file. both of these are for the analysis itself. So you can pass in, I think, the only one really of interest to us here is the prior file, is that one that you can specify. Now, it's a good point, and it's a potential future improvement is we could add an injection prior file in which you could pass in a different prior file to do injections from than you would when you do the analysis. At the moment, if you want to do that, so you want to basically draw 100 simulations from some particular distribution and then analyze them with some different prior, the way to do that is there's a Bilby pipe create injection file executable. And so this thing takes as well a prior file. So it's up here, the file name. So you pass that in and give it 100 injections. You then specify, so that then basically generates an injection file. And then in the injection arguments, you then specify your injection file here, and that will allow you to do that. So you can do what you're sort of suggesting. It's just one extra step, which is to first create an injection file, and then that gives you a whole bunch of different options. Like you can actually run with different waveforms and things like that. Okay, I think that then got us through most of the questions. So yes, exactly, yeah. Okay, so that then is the ini file. So the task for those following along is save the contents of this in a file bbh simple example.ini. So then I've sort of discussed the parallelization option. See, just quick question from Aditya. The -F option in Bilby is the name of the output file and not the. Okay, sorry, I was maybe not reading that properly. So yeah, that is the file name it saves. Thanks, Aditya, for catching me on that. Then it's the positional argument. So you just give it as the first argument. So you would do something like Bilby pipe create injection file. Well, in fact, let's actually just do this. So if I head to the GW parameter estimation workshop and then the pipe examples. So have this BBH simple example prior, which I'm going to talk through in just a second. But you can, so if I do create injections, BBH simple example.prior, and then let's ask for 100 injections. This is going to run, and we'll then see injection.dat. And so this is now a DAT file with all of those different injections put out. You can then change the file name. So if you wanted to call it, and so -F, my injection dot dat, then that will then call it my injection.dat instead. And so you can see those two there. So yeah, thanks Aditya for catching me up on that. It's good to have people who actually know what's going on watching us along. Okay, so let's then get to the prior file. So the prior file is, as I said, we just specified this line prior file equals this thing. And as I say, it's pointing to a file on disk. Either relative or absolute path is fine. And this is the contents of that file. Okay, now one thing to note here is, so I've, in this example, this is intended to be a fast, one that we can run together online. But you see here, so to do that, I've set, lots of things constant. So it's a non-spinning, that's all of these. We've set the masses. It's using a uniform and co-moving volume luminosity distance. And this shows you that you can access any of the priors available within Bilby. So you can either do that by specifying the kind of Bilby path, so bilby.gw.prior, and then specifying the usual. So this is essentially just Python. So you need to make sure that the brackets are closed and things like that. Or for ones which are defined, so uniform signs, the ones which are all available in bilby.core.prior, you can just use those directly. So you can say sign, and that's just a nice, easy shorthand. So all the core ones are available sort of in the first instance here. So, okay, so then the task is you just save the contents of this file to bbh_simple example.prior. Okay, So we've kind of gone through most of this, but let me just reiterate some of the different options that are sort of available, just because it's, it's a new language, if you like, these ini files. So you have key equals value, where it's a very simple, so it could be a string like Dynasty, or it could be an integer or a float, whatever you want. And a lot of the time it should complain at you and tell you if you've got one of those wrong. Do watch out for sort of trailing commas and things like that. Those tend to trick people up quite a lot. It can also be a list. So for example, detectors equals h1, L1, and that will get interpreted correctly and read in. It can also be a dictionary. So you have these sort of curly braces when it's a, usually these things are either called sampler quargs or -dict. And so that should be pretty explanatory. And the contents of that can be actually quite complicated. So you can have lists, you can have sub-dictionaries in it and all sorts of things. Although, this is, we've done our best to try and have as much different input as possible, especially as things like sampler quargs get passed directly to the samplers, and those have quite complex input. But this is a case where things can fall over, so just be sort of wary here, but you should know quite quickly if that happens. And then the final easy one is a Boolean. And so in general, all the Booleans are false unless you provide them as Gaussian noise equals true, or of course you can change that to false if you don't want to include it. Okay, so now we can run the example. So hopefully, let me do this along with you. So I'm just gonna open these things. So we should see here, so I have all of these, of course, available. In fact, I'm not going to do this like this. I'll just do this in one screen so it's a little easier to follow along. But importantly, if you're following along, you should have two files specified. So bbh_simple example.ini and bbh simple example.prior. Okay, so then if you want to run this, you do Bilby_pipe and then the simple example.ini. Okay, and that's it. You just hit that, and this is now going to run. Okay, so let's just take a quick look at this output. So it tells you a whole bunch of things as we go through. I won't go through all of this in detail. I just want to highlight some of the important parts. The first one is the versions. I really recommend people do just check this, especially if you run with lots of different versions of code. It's useful to make sure you're running the right thing that you're expecting. So always check that. It will then tell you sort of printouts of things that you've put in. And there'll also be printouts of things that you didn't put in, but which chose to be default. So for example, we set the trigger time to be 0. In general, we can set the trigger time as we want, and we'll see that later on. But if you're ever sort of confused about what something is being set to, these logs should contain that information. So as an example, it says no injection file found. I'm generating one now, and then it sort of generates an injection file. So generating injection file here. And all of that sort of output. Okay, so then some other printouts, things like priors is another one. This is a useful one to check. Make sure it's what you expect it to be, and then it will finish up and it will say, okay, DAG generation is complete. If you want to submit the jobs, run this. So it says Condor submit DAG, and so for those of you familiar with HD Condor, this is how you submit these DAGs, and it points you to this file here, which we're gonna take a look at in just a second. And it also tells you there's an overview page available, which you can look at. It's a useful sort of HTML file with all the different results in it. And I can show you that in a bit once I've run this. So let me just remind myself what I wanted to go through this. So this, all the output is stored here if you want to look at this sort of offline. So if you're following along, run that example and check that you get the right output. So to be clear here, this has not run or submitted the job. It only creates the files, and you saw it take a few seconds to do. And so, we haven't run the job yet. So what we can do is just familiarize ourselves with what the outputs are. So I'll do this kind of interactively. It's a bit more interesting. So if we look in this out directory bbh injection, so this is the thing it created, we'll see a few different things in here. So there's a data file. This is going to be empty right now because we haven't created any data. There's a set of log files. So one for the data analysis, one for data generation. So in general, the way that Bilby pipe works is it first does a generation step, creates the data, That typically takes just a few minutes, and then it does an analysis step. And the reason it's split up like that is simply because you may often run, several analyses on one generation, and so it makes sure that you sort of don't reproduce the same computing, or reduce the amount of computing that you do, and don't sort of do redundant computing. We then have a log for the results page. I'll talk a bit about that later on. The result is where everything is going to end up. So that's where the main Bilby outputs turn up. We'll then have a results page, which has all of the results in it, of course, with sort of outputs from a code called PE summary, which I can also talk about in a bit. And then the thing which is actually populated at the minute is this submit directory. So if we look in submit, we'll see a whole pile of different outputs. In fact, I think actually it's a little easier if I just show that in this in the README page. So there's 4 different ones in this example. If you run with different options, you'll have different varying numbers here. There's a few which are always there. So the first one is bash underscore BBH injection. This part is the label. This part is always there. So this is actually a bash file which contains everything you need to run the jobs. So we can have a look at that. So if we look at the bash file, you'll see, so it has essentially, these lines here which point to the exact executable which is going to be run, and the output. So if you ever want to sort of just run one step of it, you can copy parts of this elsewhere and run. So say you just want to run the generation step, you can just copy that, or you want to change some of the inputs to it, for example, you can copy that and do it elsewhere. We then have a set of submit files. So these ones are the ones which are, for each job. So you'll have a submit file per job. We have one generation job, one analysis job, and we always have this DAG file, which is the main HT Condor DAG submit file. And we can have a quick look at that. So here you'll see, if you're familiar with these DAG files, they have these sort of this output. I don't want to go through it in general. There's just a lot of text there, but it tells you things like the job dependencies and things like that. Okay, so as you've seen, the default is to run on HT Condor, and that's because most of the jobs that the developers run, we're using LDG resources, and so you can, if you just want to use HT Condor, you just submit things with that line. So this is the line which was printed out at the end, telling you how to submit. So Condor submit DAG. And then that DAG, so it's always the DAG file that you want to submit. You can also just add the -- submit file, submit flag, and this will submit. Now, if you're running this locally at home and you're not on HT Condor or you're on a Slurm cluster, you're going to get some complaints about the fact that you don't have HT Condor installed. So there's 2 options here. So one is, okay, if you're using a Slurm cluster, then we do have support for that. A kind of caveat here, which I should have added, is please use version 1.0.1 of Bilby Pipe, which should be released now. I should double check that. I can do that after this. So that has some improvements to the way the Slurm interface is done. And there's some documentation on exactly how all of that should work. So I recommend, you look through this. With Slurm, it's very specific. Okay, Nikhil confirms it is released. That's great. So there's some, Slurm clusters are generally, there's no uniform way that they're set up. So there's sort of, you need to activate environments. You often need to sort of specify things like accounting, which is always done on a very specific cluster by cluster basis. So there's a lot of setup with that. And so I haven't tried to include any examples here, but hopefully the documentation is sort of sufficient for you to get going with it. But if you have any questions, obviously ask away. But then what we can do today, and especially if you don't have access to one of these clusters, is just run things locally. And there's 2 ways to do this. The first kind of easy way is you add a -- local flag. So that's like this. And this is really something that I developed during testing just so that I could run things. But it actually turns out it's really useful if you just want to run simple jobs. You just run this and do it on a head node or do it on your local computer. The other option is using the bash file. So you can look at the bash file, copy out bits that you need, or just run the whole thing entirely like that. And I should also add, if you're on a cluster which isn't Slurm or HT Condor, There's a few other scheduling environments out there. You can use that bash file to set up your own submit script. So, you just copy the relevant parts and put in what's needed. And the bash file tells you things like the parents and child dependencies. Okay, so then the task is, to run this with -- local. And so we've set this up so that this will run pretty fast. So I'm going to do that here, and we can watch the outputs as we go. So add -- local flag, I hit enter. Okay, so the first thing that happens, so I'll go through this, is the first thing that gets output is the same thing that we run Bilby pipe. And then that finishes up. So we finish that right about here. And then we say, okay, we then jump into the generation step. And so, okay, I appreciate there's a lot of output here. I'm not expecting anyone to read any of it, but I'm just kind of giving a broad overview. You'll see the kind of output that we expect when we're doing a simulation. So there's things like I injected a signal in H1. Okay, it had an optimal SNR of 1.32. So this isn't going to be a particularly exciting injection. And that's mainly because the luminosity distance is so large. So it was 3,000 or so. And the mass, well, the mass is a fixed. But okay, you can, this is a random draw from the prior. We'll see how to change this in the future. And then, so once it's done that, it says completed data generation. And we then jump on to the analysis. And this will print out lots and lots of output. Again, priors get printed out. And you'll then see, okay, so with this one, I'm using multiprocessing with 4 processes. Okay, and then we see this output here. So this one here is the one that's really interesting. So it says D log Z is 0.2, which is greater than 0.1. So this is actually the convergence criterion of Dynasty. Once that drops below 0.1, what it's saying is that I've reached the point where we consider things to be converged in this netted sampling. And we have this nice criteria that the amount of evidence left, an estimated amount of evidence left is just 0.1. The log Z ratio then tells us that, okay, we found something, but not very much. And this is what we expect because the match filter SNR is so low. And there's a few other outputs, which I'll go through in detail in a bit. Okay, so whilst that's running, let me just check the questions here. So, okay, Aditya says the Conda forge is still at 1.00. Aditya, that's a very good point. So I have to manually update the Conda forges, and I think that's waiting in my GitHub inbox at the moment. So I will get on that and have that done in the next day, maybe after this call. And then Shashvas says the expected SNR had a complex piece. Is that expected? Yes. So this was a long and complicated discussion. So the SNRs we give is as their sort of complex form rather than taking the absolute value of it, simply because there is kind of phase information there which some people use, but really just take the absolute value, and that's really probably all you're interested in. So I can just scroll up so we can see that the match filter SNR. So the optimal SNR is just a it isn't a complex number, but the match filter SNR is in general a complex number. But we people generally just take the absolute value of it and report that. We just keep it as a complex number in case someone wants to use that phase information for some reason. Okay, so once that D log Z falls below 0.1, it will then finish. It will tell you the sampling time. So it was 2 minutes, 31 seconds. And we then say, it then basically does a few kind of follow-up steps. So if there's marginalized parameters, it will reproduce those marginalized parameters, as we saw yesterday. It will generate the skyframe parameters. These are there's various different skyframe parameters that you can sort of convert RA and DEC into. So that's just that. It also computes SNRs for every sample. These are all things that we saw yesterday. One point on the parallelization is that if you're using the NCPUs option, so request NCPUs greater than 1, that is implemented so that it will actually parallelize these steps as well. So you'll actually get a speed up in terms of the, in particular, the marginalized, recreating the marginalized posteriors can be quite timely if you have tens of thousands of them. And so, in general, it speeds things up in 2 senses. Okay, and then it finishes up, produces the usual sort of output telling you how many samples it has. So it has 5,000 samples. And the log base factor isn't very compelling. Okay, and then there's, this is the regular output from Bilby. So, okay, so now we can look, and so what I'm going to do is I'm going to open this in Google Chrome right here so that we can actually see this as, especially if you're using an LDG cluster where you have access to a web interface, this is more what things look like. So if we go on the out directory here, let me make this a little bit bigger. It's sometimes worth kind of going through some of these. So the data has, it makes me want to increase the page, the font size for every page. So the data directory now has two different things in it. So it has the injection file. So that's the thing it created kind of on the fly. And this details exactly the injection that was done. So you can see this was the luminosity distance. And I think the other one that we had was the phase, perhaps. I can't quite remember. Oh, no, sorry, it's the inclination theta jm. And then it has this data generation dump.pickle. So that's where all the raw data gets stored. So things like the PSDs, the strain data, all of that is just in a Python pickle file. You can open that up and you'll find the interferometers, the Bilby interferometer objects, and you can pull out all of that information if you need it for sort of any purposes. So the log files aren't going to be populated here because we ran things locally, but if you run this under HD Condor or Slurm, those will now be populated. We then have the result. So the result has all of the kind of information, interesting information in it. So all of this, by the way, is available. Let me just clean up my tabs a little bit. No, I can't actually delete tabs because of Zoom. So all of this that I'm going through, if you want to follow along, is available in the README as well. So just for future reference, you can see all of this. But I wanted to show you in sort of so you can follow along as well. So in the result file, there's a few different things which are output. So the main one that we're interested in is this result file here. So result.json, okay? It's always the result.json file that stores all of the metadata, things like PSDs, injections, everything else, along with the result. And you can read that in using the Bilby read-in result that we saw in the tutorials yesterday. So that's just a regular Bilby result file. There's a few other things. So there's two other pickle files. These are basically for the Dynasty sampler. We store that just in case it's useful, and a resume file. So if your job is interrupted after some time and then you restart it, that resume file makes sure that you pick up from where you left off, rather than repeatedly sort of starting from scratch. One thing to sort of mention on that is we write that roughly every 10 minutes or so, and it's also written when things exit. If that is sort of problematic, you can change that. There's an option in Bilby Pipe to write that on a longer time scale, so say an hour or something like that, and that may change in future as we're finding, I think 10 minutes is a little bit too short a period. There's also a samples.dat file. So this is a regular DAT file just of the samples. This is output during the run. And the idea is especially if you're doing a very expensive run, you might want to just check how it's going as it's sort of sampling. But what you'll notice is it's a very limited set of samples. So it's only the things you sample in. And if you're using sort of marginalizations, none of those will appear. So do not, try to avoid using this for sort of results in the end. You want to use the JSON file, which has everything. This is mainly to use, say if your run is, at dlog 0.5 and it has 3 days left to run and you just want to check that it's, producing something sensible. This is a sort of useful tool. We then have 3 plots that it produces. So these plots are specific to Dynasty. For other samplers, you'll find other plots with similar naming. But I want to go through these. So the most interesting and most sort of important one is this trace plot. So if we click on this, we can see that it's okay. So it's essentially railing the luminosity distance up against the upper boundary, and that's because it's a very weak signal. So it's trying to say, okay, there's really nothing of interest here, and it's found something for the inclination. But these plots get generated on that 10-minute. So every time it checkpoints, these plots get generated. And it's useful to kind of watch them and just check that it's finding something. And so these, I recommend people have a look at these, especially for sort of convergence issues. There's 2 other plots, which I'll talk through just because we have them here, but they're not so useful. So the first one is the stats plot, and this tells you things about the number of calls that were made. So in this case, it's very easy case. It didn't actually do anything of much interest. It was using about 100 calls per iteration. And then things about the bounding and the scale. Those aren't so interesting here, but you'll see when you do sort of proper jobs that get, take several hours, and the scale parameter will generally get smaller as it sort of samples, and the bound will go up. That's the bounding ellipsoids part, by the way, is how many bounds it's made. Okay, and then the final one is the run plot. So this one is useful, again, as a sort of check of the sampling. So this tells you about things like the likelihood evaluations. And so what you really want is this to be nice and smooth. If you see lots of wiggles in it, it tells you that you're sampling, you haven't sort of smoothly sampled the likelihood up to the peak, and things like the importance weighted PDF and the evidence estimation with some estimate of the error. Okay, could you explain bounds in slightly more detail? Is something specific to Dynasty? Yeah, I can. So the one thing I'll just say before doing that is, so I've put here a description of these, and there's links to the Dynasty descriptions, which are much more sort of involved and go through detail. So if you want to get into this, please head to those links. But let's talk through this bound. So we can. I just need to get to here. So it was the stats plot. Okay, this actually is very interesting. Let me just see if I can find an example of a more interesting job. Sorry again for doing this online and not having something kind of ready to go. Probably not that. Let's go for the 5914. This is a good choice. Okay, so let's look at this stats plot. So this is what you'll see. This is a run on 5914. So the bound, you'll see basically at some point, it's running, and then suddenly you see this phase change in this plot, and suddenly things start to happen. What's happened there is that, so as I described yesterday with nested sampling, you start off by drawing points from the prior. Okay, and so during this kind of period here, you're drawing points from the prior and using those sorry, my headphones are getting caught up here, to update that lowest live point. So just as a reminder, with nested sampling, I throw 1,000 live points down, evaluate the likelihood of them, order those in a list. Lowest log likelihood point, I'm going to try and replace with a new point drawn from the prior, which has a higher log likelihood point. So at first, what I do is I draw points randomly from the prior, okay? And I pick one, random point is if it's higher log likelihood, okay, I remove the old point from the list of live points and put the new one in. So it's always a list that's 1,000 long. Okay, so then at some point, what happens is that the efficiency drops, okay? And actually, this is probably a useful point to say how you see this happen in the sampling. So if you look at the output, so the output of Dynasty looks like this. So we see a whole bunch of different things, but importantly, this one here is the efficiency. And so this is the first few iterations. So you can see we're at 136 or so. So there's a few above this. But the efficiency will, it generally starts off high and then goes lower. Here it's actually started to increase a bit. So you get wobbles in it, but in general it drops. When the efficiency in Dynasty drops below 10%, it switches from this picking points from the prior to picking points from a bounded ellipsoid. Okay, and so that's the phase change which happens. You can control that 10%, by the way. That's a user settable parameter. So what then happens is it starts to say, okay, rather than drawing points just from the prior, I'm going to draw points from a set of bounding ellipsoids. And this bound basically tells you how many you have. And there's some noise in it, but you see it generally sort of increases linearly as you add more as you add more bounding ellipsoids in order to sort of better get this shape. And the other two plots here are just the number of calls. So that's, you see that if you don't use bounding ellipsoids, what happens is this kind of just rockets up exponentially as it gets much and much harder to evaluate a new point from the prior. So in this case, actually, it's probably worth running a little. 10% is probably a little too conservative. You could have run to maybe 5% or something like that. But the 10% default works most of the time. And then after that, you do it from these sort of bounding ellipsoids, and this is sort of much better behavior. And then the scale. Okay, since we're on this plot and I've gone through the other two in detail, so the scale is about, so once you have those bounding ellipsoids, as mentioned yesterday, you don't just pick points from them, but you pick points and then do a little random walk. And this is what we find we need in order to capture the real subtle features of gravitational wave posteriors. And when you do that random walk, there's a scale parameter in the proposal, and that's automatically updated by Dynasty, and you see that this is the value of it. And you see it, so it gets smaller basically as you go on, and that's because you're doing sort of taking smaller steps. Okay, hopefully that was a sort of a run through that may have been a little too detailed for some folks. So sorry for that. Hopefully we all sort of stuck together. Okay, so then how are we doing for time? Okay, like an hour or so. Okay, so I think I should be done in about 20 minutes or so. Is that okay, Shashvath?
Yeah, absolutely, as long as you need.
Okay, great. Then that will then leave us an hour for sort of breakout rooms and things. Okay, so then I wanted to go through the Dynasty output, because again, all of this is, you should be trying to check this output as you go. And so the more you can kind of know about what it means when it's printing stuff out, the better you'll be able to diagnose problems in your own runs. So I wanted to go through this in detail. So I've put sort of the parts to it here. So this is it, as one line, and this is it sort of broken down. So we have essentially the number of iterations it's taken. You then have the time taken so far. And so I put a note here. So on HD Condor jobs, we actually restart jobs after about 4 or 5 hours. And this is because HD Condor wants us to. So that number doesn't always reflect the duration of the job. It's the time since the start of this run. So if you're resuming an old run, it'll zero out at the start of that. You then have something which tells you about the number of iterations per second. And in general, you find that this tends to sort of vary massively at the start and then sort of level out. And it's roughly speaking something about the sort of CPUs you're using and things like that. So it can be a useful number to just keep track of. The bound index, so this monotonically increases, and that's shown in that plot, and you can read more about it in the Dynasty documentation. Then NC, so this is the number of calls used in the last iteration. So the bound and NC, those are both sort of shown in this plot here, so you can see them graphically and also see them as they update in the printout. This number then is very useful. So this is the number of calls taken. And so we just round this because it's just a useful number. But roughly speaking, we tend to find that you need something like 10 to the 6, 10 to the 7 iterations to do a sort of typical processing CBC system. So this is very useful because you'll know, if you see that this is going up to sort of 10 to the 8, 10 to the 9, you can roughly guesstimate how long that's going to take. So that's just useful to keep track of how many calls, because that's where most of the cost comes from. You then have the efficiency, which I already talked about. So that's the number of calls, roughly speaking, or the number of samples which you're producing to the number of calls. And then we have the log Z ratio and the D log Z, which I've already gone through in detail. And I'll just highlight that the bit on the end of that is the estimating remaining evidence. So in this case, it was 3, but in general, it will be 0.1. Okay, yeah, and then one final point on those evidences is that in general, if you add together log Z ratio plus D log Z, that is the current estimate of the final evidence. It's worth noting though that so while log Z ratio monotonically increases, D log Z does not monotonically decrease. It will decrease, but you'll sometimes find it jumps and it increases, and that's effectively where the sampler has found a new region of parameter space with higher log likelihoods, and so you have better sort of overall evidence. And you'll see that in the trace plots. You'll see it basically start to funnel into a point and then suddenly jump. In general, that's sort of not good behavior, and it speaks to maybe increasing the number of live points. So you would find that earlier before it starts sort of funneling in, or running. You want to run maybe a few jobs in parallel just to make sure that you have caught the real high likelihood points. For gravitational waves, this doesn't tend to happen so much, but for other jobs, I've seen it be quite sort of problematic if you have sort of very narrowly defined posteriors and things like that. Okay, so we went through the output files. So it's here with the description in case you want that in future. So we can then just scroll through these things. So this trace plot, by the way, is not a good example of what things should look like. So actually what I'll do is I'll jump to the trace plot for 5914 so we can see, you know, this run took, I think about 24 hours or so. Apparently I can't zoom in any more than that. But here, so this is the chirp mass, and you see it funneling down nicely, and the mass ratio is sort of well measured and spins and things like this. So this is what things will more typically look like. And you'll see, you know, some parameters. So this is the inclination, for example, are sort of less well measured, and you get some sort of stratification, but in this case, it looks good. And then these are all the calibration parameters, which are added for production runs. Okay, so then let's move on. So we talked about prior files. The other thing that I wanted to talk about was we have a set of default priors available in Bilby, and this is just because we don't really want to port around, you know, priors for every single analysis. There are sort of well-defined sets of priors that we might want to use. And in general, we specify these on the duration of data. So they are intended to match the duration of data. You can use separate priors for different durations, but in general, if you use the same duration and the same prior file, you'll make sure that you don't have templates which sort of come out which don't fit in the duration and things like that. So we can click on those, and that will take you to where those are defined in Bilby pipe. So the path is right there. And so you'll see a lot of things are sort of constant between them. So these are set up for processing waveforms. So they have full spins, and the main thing which is changing is the chirp mass and the distance estimate. So we change the distance in order to the distance maximum, in fact, just so that for the low mass ones where you don't really expect to see things out to 5 gigaparsecs, you aren't gonna sort of, you know, there's no point looking for BNSs at 5 gigaparsecs. So we set a lower maximum distance just to improve convergence, so we don't have such a large prior. So those are the two things which kind of change. Hand up from Apratim. Yeah, please go ahead.
So I have seen this before. So can you explain why the mass priors are so broad? Mass 1 and mass 2.
So the chirp mass prior?
No, mass 1 and mass 2.
So that's with chirp mass or the component masses, I should
the component masses.
Get clarification.
The component masses.
Okay, I'll take that to just be a general why all of the masses are so broad. So the main reason is that, you know, if you're analyzing a specific event, so say you're analyzing 5914, you know, we know the chirp mass very well because the online detection pipelines have found it. So in general, so Abratim clarifies it's the component masses. So in general, you know, we don't know that a priori. So you know, we have this is really our uncertainty, actually. You know, if you give me a random data segment and you ask me, okay, you know, here's 4 seconds of data from Hanford, what kind of mass systems are in there? Unless I go and run PyCBC on it, or, you know, any of the other pipelines, I don't know what's in there. So my prior is actually this broad, right? And in fact, it should be even, you know, broader than this, perhaps. So the reason then that we, you know, so we set these up to kind of work on any given segment of data. And then that ensures that you will, you know, capture it and you won't bias things. Now, sometimes, in fact, these are actually not broad enough. And often, you know, with sort of online runs, we see things sort of railing up against the chirp mass boundaries, at least, not the component mass boundaries. So that's really why. I mean, you can, you know, these are just defaults, which are supposed to take any, you know, work for kind of any segment of data. If you know more, you know, put it in. But do be wary that, if you constrain things too much, you are kind of using the data twice, right? Like if you have output from PyCVC, which tells you the chirp mass is, 20 plus or minus 0.1, and you put your prior as 20 plus or minus 0.1, well, you're using the data twice, once to set your prior and then once in your prior. Does that make sense, Abratim, or did I not quite get your question?
Sorry, can you hear me? Hello?
Hey, yeah, I can hear you now. Yeah, I can hear you now. Maybe my internet dropped out. Did that make sense to you?
Sorry, why I wanted to ask you this question is because the priors are generally on the chirp mass and the mass ratio here. The masses, the component masses are constrained. So you're basically reweighting at the end. So why do you need such broad priors?
So, okay, so now you get to another interesting point, which is the choice of where your uniform priors are. So we choose uniform priors in chirp mass and mass ratio, and then we put cuts in the component masses. Now, and this is counter to what Lal inference does, for example, which is uniform in the component masses with cuts in the chirp mass and mass ratio. So I want to make something very clear to people, which is that neither of these priors are really uniform in either thing. As soon as you put constraints on something else, then you end up with basically you end up with some sort of shape and structure. So it's a useful exercise to go and take these priors and plot them in terms of mass 1 and mass 2 after you make those cuts, and you'll see that things get very sort of complicated. So constraints change the shape of things. So neither our priors are our priors are not uniform in chirp mass and mass ratio once you apply the constraints, and the Lal inference priors are also not uniform in mass 1 and mass 2 after you apply the constraints. So one of the options that we provide in Bilby is the option to reweight to the Lal inference prior, basically. And so there's this flag here, convert to flattened component mass, and that's the reweighting which Apratim was asking about. So if you do this, this will then end up with things being identical to, well, identical if you set the same limits to Lal inference. And so that option is available to people if you need it. But yeah, so you need to put some constraint here in order to do that reweighting. I think that's maybe the key answer here. Did that make sense, Everton? Okay, great.
Yes. So just one line clarification. So if I'm using that particular flag, then I can use a lower, a narrower bound on the component masses. Is that?
Yeah, you can use any bound that you want. And in fact, if you want to match to Lal inference, for example, you need to make sure you use the exact same bounds in order to have the same prior.
Okay. Okay. Thanks.
Yeah. And the other thing I'll just say is, it's easier to sample in chirp mass and mass ratio. Lal inference also samples in chirp mass and mass ratio, but they apply Jacobians in order to allow them to set the priors uniform in component masses. It's something that's ongoing in Bilby, but we don't have what's hard about it is we don't have a way to apply it uniformly across samplers. And so that's what's held it up, and we use this reweighting instead. So yeah, that's where we're at with it. Okay, so if you want to use one of these default priors, you simply specify prior file equals 4 seconds. You don't add dot prior or anything like that. If you add anything after that, it will try to look for a local file. So just 4 seconds is all you need. Or if you're using 128 seconds, 128. Okay, so let me then get on to sort of accessing data. Okay, my internet is going a little unstable, but I assume people can still hear me and carry on. Okay, I see a question. Can we define our own frequency domain source model in Bilby pipe? Yes, you can. So I can, well, if you just look in the help output, you pass in the name of the frequency domain source model, or any Python path to a Bilby source function in your installation. So if you have something set up, you just pass it in there, and that should work. Okay, so now accessing data. So as I said earlier, when we do, if you're running on a local machine or something like that, you be able to access data remotely. Now, everything I'm going to show you here uses GWOSC open source data, in which case you don't, you don't need to sort of log in or anything like that. If you are a LIGO member, or like LIGO Virgo Kaggle member, you may be asked for your login details if you want to access sort of closed data, and that's specified through the channel, and we'll see how that works in just a second. So okay, so let's go through this then, and the example now is going to be running on 5914, and the key is that we need to add this trigger time and channel dict. So okay, so this is then the ini file. So things are roughly the same. So we have accounting, we have label, out directory, detectors, sampler quarks, all of these things. And then here's where things change. So the first thing I've changed is that I've put in that we're going to use the 4-second prior. So this is the one which is appropriate for 5914. We then have, okay, so the trigger time. So in Bilby pipe, we have the ability to specify trigger times by a string pointing to the event. And if so we use GWOSC essentially to convert that string into an event time, and this is just a kind of convenience, but you can alternatively specify the trigger time exactly just as a float. So you'd need to just uncomment that. So that's one part, is you need to specify this trigger time, and the other part then is you need to specify the channel dictionary. So if you want to use just the open data, you just specify a dictionary where you have the detector name, so H1, a colon or an equal sign, and then GWOSC, all in capitals. And that will then make sure it pulls data from the open data that's available. If you want to use a channel, you just simply put the channel name here without any of the detector sort of part in the front. So if it's, GDS strain or something like that, that's the online data for LDG users. Okay, so that's that's the ini file. You can run that, so feel free to store that and run it. But a warning, this will take 12 hours or so, because it is really a full analysis of 5914. So you may want to do this on a cluster, and you may want to use the request CPUs option and things like that. Okay, so then I wanted to do just one final example, which was injecting a signal into real data. So we've done injecting into simulated data. We've done analyzing real data with an event in it, and we now have the final piece, which is inject a signal into real data. And this is just an example of how you do that. So again, things are much the same. You have the same setup in that you put the channel dictionary there. You then want to specify a trigger time. So this needs to be, some time where there is data, and you'll need to do, if you want to choose things randomly, you'll need to do your own sort of data quality checks that you're not injecting into bad data or where there isn't any data, which will cause it to fall over. But then the final thing I wanted to show was just that, so these two lines, if you add these, injection equals true, and then here we give an injection dictionary. So in difference to what we did before, which was to draw a random point from the prior, which is what would happen if you didn't put this injection dictionary here. In this case, we simply specify the injection directly. So it has a chirp mass of 17, mass ratio of 0.3 or so, and all the way, you need to specify all these things. The one thing to be very careful of when you're doing this is this geosent time. So this you really want to match to the trigger time, because this is the merger time. So that needs to match, otherwise you'll end up with sort of very odd results where you have a signal, well, you won't inject your signal into the data. It will be somewhere off and do sort of strange things. Okay, so that was kind of it, and again, this one will take some amount of time to run, as it's a full analysis. This is not 5914. This should be of the injection, of course. And so Nirvan then asks, we can also specify an injection file in case of real data, right? Absolutely, yeah. And you can give an injection file and a set of GPS times and inject, into the set of times and all sorts of things. And then Mukesh asks, can it also take an XML injection file? So no, it can't. So the injection file itself, if we look up in the part here, so actually it doesn't say this, but it needs to use a JSON or DAT file. But if you have an XML file, then you can use this XML converter, so Bilby pipe _ XML converter to convert from the XML to a JSON file or a DAT file. Okay, so then I just had a final comment, which is on paraspectral densities. And this was, something I sort of alluded to earlier, which was, if you, by default, just use the 04 ones. If you want to do things, if you want to be specific about which PSDs you want to use, then you'll need to specify the Psd Dict, and it looks something like this. So it's just H1, the detector name, colon, and then a path to the PSD. And so this is, for most analyses of events, the recommended LVK way of doing it is to generate a Bayes wave paraspectral density. And so these take the common file formats of those, and you just pass that in. If you have an ASD instead, we don't have an ASD dict method, so you just convert your ASD to a PSD. It's something we could add, but it sort of seemed just like an easy step, and most people run with PSDs anyway. Okay, and then there is a sort of comment here about, if you're running on just data and you don't have PSDs, you don't want to use Bayes wave PSDs, we have the infrastructure to generate PSDs from the data using the usual sort of averaging methods. And so there's details there about all of the different settings. Thank you, someone, for annotating things. I don't know what's going on there. Okay, but that was it, I think, yeah, for this go through. So I guess maybe it's a good idea if we pause for sort of quick questions. If there's anything more detailed, I suggest that we leave that for the interactive session, especially if it's sort of details of how do I do this or how do I do that. But if there's any sort of broad questions that I can answer, maybe we can just do that quickly and then go to the interactive sessions. Is that best, Shashvath?
Yeah, that sounds good to me.
Okay, great. So is there any quick sort of broad questions that people have? So Raymond asks, is this workshop recorded? I don't think it is, right, Shashvath?
I think it should be. It was recorded yesterday.
Cool.
Naveen, are you recording this?
Yes, Ashwin. Yeah, we are recording.
Yeah, so it is being recorded, and I guess it will be available on the ICTS website at some point, right?
Yes, yes.
Okay.
Oh, cool, neat. I didn't know that. That's awesome. Okay, well, in that instance, if there's no sort of quick questions, I suggest we go to breakout rooms. And I think that what I would suggest people do in breakout rooms, so I've gone through all of this material, but no doubt you have your own workflows that you kind of want to try out. And I suggest that you either go through this or get installed, get things set up, use the experts to kind of help you understand the subtleties of it, and maybe start just trying to create some workflows and ask questions. So yeah, so I'll pass back to Shashvath to organize going to breakout rooms.
So yeah, Naveen, could you do as we discussed, like 4 breakout rooms with
Okay.
the experts in each of the rooms?
Yeah, fine. I'll do that.
Yeah. Thank you.
Yeah, sure. So obviously we're like at the hour. So I would just like to say thank you to Shashvath and Aditya and Ajith and all of the tutors. It's been pretty fun. I've enjoyed myself, and I hope it's been useful for people. the materials will remain in the same place, and I'll fix bugs in them, but otherwise leave them as is. So feel free to, you know, use them as you want in the future. And if you find issues, by the way, please just, like, if you, when you're going through, you find a bug, open an issue or even a merge request to fix it would be really fantastic. So welcome that. So from my side, yeah, thank you very much. And you know, it's been a lot of fun. So back over to you, Shashvat.
So I just very quickly wanted to bring up a few small things. So one is like Naveen mentioned, this workshop was being recorded. So are you okay with the recording being on the ICTS website? It's completely up to you.
Yeah, that's fine with me. No problem.
Okay, great. The other thing was regarding the, this thing that Hemant brought up. About keeping in touch if people had questions, comments. Is there like a channel, a Slack channel or something like that for Bilby that people can ask, or ping you or anybody who's an expert on Bilby?
Yes, there is. We have a Slack channel. I'm just trying to find it. It's on the main Git page of Bilby. So I'll just paste it here. If you scroll down there, you'll see it says that there is a Slack channel. There's also for LIGO folks, there is a Mattermost channels, Bilby Help and Bilby Development, which you're welcome to join. And then there's a Slack workspace. You need to email one of us for the email the support desk to request an invite. Or you can email me and I can add you. So I don't know how we want to do that, but yeah, if you email me, then maybe that's the easiest thing, and I'll just add you and make an invite.
Okay, that's great. And finally, I just wanted to ask. So I know that there are, there was a lot of enthusiasm for this workshop, and some of the participants are actually not a part of LIGO. Nevertheless, if they wanted to contribute to Bilby in a certain way, is that possible, or do they have to be members of LIGO?
I'm really sorry, Shashvat, it cut out there again. My internet is just really dodgy today.
Oh, no worries. Let me repeat. So I just wanted to ask if there are participants who are not part of LIGO but are still enthusiastic about contributing to Bilby. Is that possible?
It is possible, and certainly if we have, so at the minute it's slightly difficult because we use git.ligo, but if we have lots of enthusiasm for it, I'm sure we may be able to move things to GitHub or something like that. So if people are enthusiastic, I'd recommend, you try making merge requests. So there's a Bilby GitHub as well, but that's currently just a mirror, but you can create merge requests there and make contributions. And it's a little bit of work for us to then get them into the code, but please just make them there and we'll figure them out as we go.
Okay, great. So I'm sure if there are participants who are not LIGO members and are interested, I'm sure they would have got that. Okay, so I think that's really all I wanted to bring up. Aditya, did you want to add anything before we close?
Not really. I mean, I just want to thank Greg for taking out his time. Yeah, and that's about it. And thank the participants for attending.
Ajit, any final comments you wanted to make?
No, I just wanted to repeat what we said earlier. Thank you very much, Greg, for doing this, and we all find it very useful. There is no doubt about that. And I look forward that this will also lead to several collaborations and many good uses of the LIGO data using this new software tool. Thank you very much.
All right, then. So let
Sounds
me.
Great. Well, thanks everyone for all the attendees as well. It's been really fun.
Yeah, I was just going to say thank you from my side as well. This has been very useful for me, and I suspect for a lot of others as well. So thank you. All right, then. So if there's nothing else, I guess we can all sign off. Have a good weekend, and thank you for attending.
Bye-bye, everyone.